Hello students, after studying this module, you shall be able to understand the basics of azulene, synthesis of azulene and physical and chemical properties of azulene. The name azulene is derived from a Spanish word azul meaning blue. Azulene is a dark blue color organic compound. It is an isomer of naphthalene having a molecular formula of C10H8. Azulene is a completely conjugated non-benzenoid fused ring hydrocarbon which consists of 7-membered rings fused with 5-membered ring, while naphthalene is a benzenoid hydrocarbon consisting of 2 benzene rings fused together at ortho position. As can be seen from the structure, azulene is a 7-membered ring fused with a 5-membered ring system, whereas naphthalene again 2 benzene rings are fused at the ortho position to each other. The chemical name of azulene, bicycle 5,3,0-decapentane, is a non-benzenoid aromatic compound, while naphthalene is a benzenoid aromatic compound. The higher stability of naphthalene over azulene is due to the resonance stabilization, since only 2 resonance structures can be written for azulene compared to the 3 for naphthalene. This is again shown in figure. Azulene is a natural product and functions as a pigment in living organisms like plants, fungi, etc. This compound was first isolated from German chamomile and later from yarrow, wormwood and other plants as an oily liquid. This compound is used in skincare products as a biocolor. This imparts blue tint and is an important ingredient in the beauty products like soaps, moisturizers, etc. This also reduces inflammation in the skin tissue and also has a potential to protect the skin from free radical damage. Azulenes can be synthesized by several methods and the various methods available for the synthesis are from adipic acid. 2 molecules of adipic acid combine together by a condensation reaction with the loss of 1 molecule of water and 1 molecule of carbon dioxide, resulting in the formation of 6-oxo-undecanoic acid. Loss of 1 water molecule again from 6-oxo-undecanoic acid results in the formation of 2,4-carboxybutyl cyclopent 1-ene carboxylic acid. Again, a loss of 1 more molecule of water and 1 molecule of carbon dioxide from the above compound results in the formation of 2,3,5,6,7,8 hexahydro 1H azulene 4-one. Further dehydration and dehydrogenation, as it is shown here in the reaction, results in the formation of azulene. From indane. It's a ring expansion method. This is the most widely used method for the synthesis of azulene. In this method, indane or the derivatives of indane are treated dropwise with ethyl diazoacetate at 130 to 135 degrees centigrade for about 2 hours. Upon completion of the addition, the temperature is raised to 160 to 165 degrees centigrade for several hours. During this process, first, carbene is generated in situ through the nitrogen extrusion reaction. As shown in the figure, nitrogen is lost here. The carbene further reacts with one of the double bonds of the benzene of indane to form a cyclopropane ring. As it can be seen from the figure, the cyclopropane ring is formed by the ring expansion reaction. After the reaction, the unreacted indane and ethyl diazoacetate are distilled off. The addition product is dehydrogenated using palladium charcoal to form a corresponding mixture of azulene carboxylic esters. These esters are then hydrolyzed to the corresponding carboxylic acids, which are then decarboxylated and dehydrogenated to form azulene. It is shown here in the figure. Here it is also seen that the carbene could have attached to any of the three double bonds in the benzene ring, leading to the ring expansion. Either of the additions forming a cyclopropane ring would not have made a difference, as the final product obtained in any of these reactions will be same as azulene. The next method is from the methylamine derivative, which is also called as Dam-Genow ring expansion. This method of ring expansion involves a chemical reaction between carbon, octahydroindene 5-yl 1-methylamine with nitrous acid. The nitrous acid is formed in situ by reaction between sodium nitrite and hydrochloric acid at 0 degrees. Here, the temperature of the reaction has to be carefully controlled. This reaction gave a carbonium ion CH2+, which facilitated the ring expansion, and further reaction with water gave decahydroazulene 5-ol. The alcohol formed is then oxidized with the help of an oxidizing agent, chromium trioxide, to form decahydroazulene 5-on. Further reaction with a methyl magnesium iodide, which is a Grignard reagent, followed by hydrolysis and aromatization, results in the formation of 5-methyl-azulene. All can be seen very clearly from this reaction sequence. Properties of azulenes. Azulene is a cyclic and a planar molecule with 10 pi electrons. It obeys Haeckel's rule of aromaticity, which is 4n plus 2 pi electron rule, where n is equal to 2. It has a complete delocalization of pi electrons, and hence it is an aromatic compound in nature. It has a substantial dipole moment, which is 1.0 dBi. It suggests that there exists a charge separation in the molecule. Each ring approximates to 6 pi electron system. After the charge separation, it is regarded as a combination of an aromatic cyclopentadienyl anion and an aromatic cycloheptatrienyl cation. Thus, in a valence bond term, the ionic structure of azulene is an important contributor to the resonance bond. As can be seen, the delocalization of the pi electrons leads to the formation of the two charged ring systems in the azulene structure. Both ring systems are aromatic in nature. Isomerization. Azulene can be isomerized quantitatively to naphthalene on heating above 350 degrees centigrade in absence of air. A high temperature heating leads to the isomerization of naphthalene, as both of them are the isomers of each other with the same molecular formula. Being aromatic in nature, they tend to undergo electrophilic aromatic substitution reactions. The electrophilic aromatic substitution reactions like halogenation, nitration, Friedel-Crafts alkylation, etc. preferentially takes place in the 5-membered ring, since it is more electron rich than the 7-membered ring system. Above, we had seen the ionic structure where the 7-membered ring system acquires a positive charge, whereas the 5-membered ring system acquires a negative charge. As a result, it is more rich in electrons. The quantum mechanical calculation suggests that the electrophilic aromatic substitution takes place at position 1 in the azulene as shown in the given figure. Further reactions give product both at 1 and 3 positions. If position 1 and 3 both are occupied, the reaction would take place at 5 and 7 positions. The position numbering is shown here in the structure. Here, for example, Friedel-Crafts acylation of azulene takes place using acetyl chloride and aluminium chloride. It leads to the formation of 1-acetyl azulene and 1,3-diacetyl azulene as shown here in figure. The electrophilic substitution reactions of azulene with isocyanates are NCO and nitrile oxides are CNO in presence of Lewis acid like zinc chloride took place at C1 position and gave azulene 1 carboxamides and 1 aryl azulene oximes respectively. 1 nitroazulene was obtained on treating azulene with cupric nitrate and acetic anhydride in red color needles, leading to the nitro substitution in the given compound. The reaction with acids and bases. Azulenes react differently to acids and bases. They are not soluble in alkali and soluble in strong acids. The solubility in acids is a valuable observation and is employed for the purification and characterization of azulenes. Azulenes get protonated in the presence of a strong acid at position 1, leading to the formation of azulenium ion, a derivative of relatively stable cycloheptatrienyl ion, commonly called as tryptilium ion. As can be seen here in the figure, since tryptilium ion is a very stable carbocation, and this becomes a driving force for the reaction to take place, and therefore the protonation of azulene is rather very simplified reaction. To summarize, azulene is a non-benzenoid fused ring aromatic hydrocarbon. This consists of 7-membered ring fused with the 5-membered ring. This is more stable than the isomer naphthalene due to resonance stabilization. Azulene is a natural product and exists as a blue color oily liquid. This compound is used in skincare and beauty products. It also reduces inflammation in skin tissue and also has a potential to protect the skin from free radical damage. Azulene can be isolated from plant sources. This, along with its derivative, had been synthesized by various methods. Few of them include its synthesis from indane and its derivative, adipic acid, etc. Azulene is an aromatic compound and hence easily undergoes electrophilic substitution reactions like halogenation, titration, Friedel-Crafts reaction, etc.